Welcome to This Explainer. Today we're diving straight into a fascinating cosmic detective story. We're going to look at how the world's top theoretical physicists are actively battling to contain one of the absolute wildest, most mind-bending ideas in modern science, the multiverse. It's a concept that has totally exploded in popularity, but mathematically and scientifically, well, it's causing some massive headaches. We absolutely have to ask ourselves this crucial question right out of the gate. Is the multiverse actually science? Because this concept threatens the very definition of falsifiable physics. Think about it. If a theory predicts that literally everything can and does happen in some universe somewhere, how can we ever run an experiment to prove it wrong? If we can't test it, are we still doing physics, or have we just wandered into a giant mathematical illusion? Here is our roadmap for the explainer. First, we'll tackle the infinite multiverse problem. Then we'll look at Hawking's final stand, followed by the fierce debate between philosophy and empirical science. After that, we'll see what happens when universes collide, decode the mathematical blueprint, and finally, try to test the untestable. All right, let's get into it. Section 1. The infinite multiverse problem. Let's start massive by looking at how our most advanced, elegant physical theories accidentally birthed an infinite problem.
10 to the power of 500. Take a second to really wrap your head around that number. It is a staggering, almost unfathomable estimate of string theory solutions. Now, originally, physicists hoped string theory was going to elegantly result in just one unique solution, a beautiful, unified theory predicting our exact universe. But instead, depending on how you fold up the extra dimensions, the math spits out 10 to the 500 possible universes. Physicists call this the landscape problem.
So, because string theory predicts this virtually infinite string landscape of universes rather than just the one we live in, critics point out a huge flaw. It kind of completely loses its predictive power. I mean, if your theory accounts for literally every conceivable version of physics, then it doesn't really predict anything specific about our reality, right?
Which brings us to Section 2, Hawking's final stand. Because there was one legendary physicist who absolutely refused to accept this mathematical chaos. Before he passed away, Stephen Hawking decided this uncountable reality was just fundamentally unacceptable. He literally said to his colleague Thomas Hertog, "Let's try to tame the multiverse." In his final published paper, Hawking set out to rein in this untamed beast, trying to transform it from wild speculation into a coherent, testable scientific framework.
To do this, Hawking and Hertog took a three-step approach. First, they revisited Hawking's famous no-boundary proposal from the early days of the universe. Then they applied holographic principles to bridge gravity and quantum mechanics, which allowed them to mathematically trim the multiverse down. They basically built what physicists call a toy model to render the multiverse finite and countable. Now, it's not the final answer by any means, but it's a massive step toward actually making the multiverse testable. Moving on to Section 3. Philosophy versus empirical science. We need to pause and ask a really tough question about all of this. Is trying to explain the fundamental parameters of our universe actual physics, or has cosmology just blurred into pure philosophy? This is the ultimate showdown happening right now. In one corner, you've got the empiricists. They are totally data-driven, demanding measurable signatures and observational proof. In the other corner, you have the rationalists. They are theory-driven, leaning heavily on the principle of sufficient reason. That's the idea that everything, even the crazy fine-tuning of our universe, has to have a logical explanation, even if we have to invent a multiverse to give us that explanation. But physicist Lee Smolin pushes back hard on this. Sure, rationalist criteria demand that a multiverse dynamically explains our laws of nature, our fine-tuned parameters, and our initial conditions, but Smolin argues that using these principles to simply assume an untestable multiverse exists, that is deeply problematic. It's a great guiding principle, sure, but without empirical data, it's basically a giant leap of faith.
Let's look at Section 4, when universes collide. Because to really solve this cosmic detective case, we have to know our suspects.
These multiverse theories are definitely not built the same. We've got a few distinct players here. There's eternal inflation, driven by scalar fields, which might actually be testable. Then there's cyclic brane theory, born out of 11-dimensional string theory. We also have the famous many worlds interpretation of quantum mechanics, where universes are constantly branching but probably never interact. And loop quantum cosmology, which proposes a pre-Big Bang bounce. The key takeaway here is testability. Some of these are locked away forever, while others might just leave a fingerprint we can find. However, physicists Orfeo Bertolami and Victor Herdero point out a massive hurdle. When you throw the quantum mechanics of the multiverse into the mix, you get some extreme nonlinearities. High energy and low energy states start mixing. You get EPR paradox violations across the boundaries of different universes. Basically, this means these universe bubbles might not stay perfectly isolated. They could continuously influence each other, which just totally scrambles the neat and tidy math we're trying to use.
And that brings us to Section 5, the mathematical blueprint. When quantum mechanics gets this messy, what's the next move?
You bring out the heavy, highly abstract mathematics to structurally model the multiverse from the ground up. Enter a concept called synthetic differential geometry. Researcher Alexander Gauss proposed using this incredibly dense math to formally build a geometry of parallel universes. What's completely wild about this is that it uses intuitionistic logic and infinitesimals. It literally bypasses standard classical logic to prove that a multitude of four-dimensional spacetimes can coexist. They are literally bending the rules of math to accommodate the multiverse.
All right, our final stop, Section 6, testing the untestable. Let's zoom back out from the intense math to the ultimate question.
Can we ever actually find the smoking gun for these theories? Well, some of these models actually do offer physical clues. If eternal inflation is right, we might literally see circular anomalies in the cosmic microwave background. Think of them like cosmic bruises, where another bubble universe bumped into ours. Conformal cyclic cosmology predicts very specific particle fluctuations, and the brain theory suggests we might even detect a background hum of gravitational waves from universes colliding in higher dimensions. We just have to build tools sensitive enough to catch them. So as we wrap up this explainer, I want to leave you staring at a really profound thought. We have these brilliant mathematical blueprints, and the brightest minds in the world are trying to tame infinite equations. But if the multiverse ultimately remains forever beyond our physical measurement, are we still doing science, or have we crossed a one-way bridge into pure philosophy? How we answer that might just redefine what physics even is in the 21st century.